Okay, so now at this point in the semester and this point in this chapter on intermolecular forces, it's really fun for me to get to explain some things that you have a lot of common knowledge of, but you maybe don't know how they work. So this is just for fun. I think it really incorporates a lot of the ideas that we've had on intermolecular forces, and so I think you'll enjoy this. So I'm going to talk about, my examples are Tide and Downy, but we'll talk about detergents and fabric softeners and how they work and why you can't mix them together, and it all comes down to these intermolecular forces, and also some of the precipitate chemistry that we talked about very early in the semester. So I use Tide, so this is the one that I went and researched, and Tide and a lot of detergents are what we call anionic surfactants, and basically it's, and I have to describe a little bit about what's going on here. So Tide has this long tail, and it will depend on what type of detergent you use. But basically, you have a long tail, and if you remember back, we talked about line drawings earlier in the semester, but I'll recap it here. Remember, each one of these corners is a carbon. So this would be like me writing CH3, CH2, 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 and zigzagging that all the way along. So each of those corners is a carbon with some hydrogens attached to it. And then we get down here to this other end that has a negative charge on it. So what we're looking at is a hydrocarbon tail and this charged or anionic end over here. And often, and it doesn't even matter what identity this has, it might be in a sulfonate in one substance, it might just be an OH group in another. But basically, this is an end of that big molecule that really likes water. So what I'm going to do is draw these as the charged head and a tail. And we call this a hydrophobic tail and a hydrophilic head. That just means the tail is afraid of water and the head likes water. And when we go to put this into the liquid water, the reason that this carbon end doesn't want to interact with the water is what? So think back to our intermolecular attractions. If I didn't show you this other end, if I just showed you the carbon-hydrogen length of that molecule, what's the strongest type of intermolecular forces present in this piece of that molecule? So you should say that it's nonpolar, because hydrocarbons are nonpolar, and so dispersion forces are the strongest type of force present here. And anytime that you have one substance that has dispersion forces, it really only likes to dissolve in other things that only have dispersion forces. They have to have similar types of intermolecular attractions. And we use a phrase called like dissolves like. Those types of compounds will interact well with other similar types of compounds. The next chapter we'll talk even in more detail when we're making solutions about this particular piece of information. So if you want more background to that, you can go take a look in the next chapter. But this end really doesn't like water. So if you think about what oils really are, they're hydrocarbons. So this would be like an oily end of a molecule. And if you have any experience at all making any kind of food, or if you spill some oil outside and you see it sitting in a puddle of water, you know that they don't mix together. Oil and water don't mix because they have dissimilar intermolecular forces. So this is the oily end, the end that doesn't like water. And then I have this other end here, the hydrophilic head, that if it's charged, we know water's polar, so we know charged particles will interact with water. And we also know that if it's something like an OH group here, it's got a polar end, that's also attracted to water. So this piece is something that has similar intermolecular attractions and will dissolve easily in water. So now with that background information, you go throw this into a beaker of water. Let's say that I'm looking at trying to, so here's my liquid water at the surface. I dump in some of my Tide because I want to wash something. And if I put those molecules into the water, they will actually form what we call micelles. I like to think about it like they're circling the wagons. All of these hydrophilic heads like to interact with the water, but these tails are oily and they want to avoid the water. So they like one another. They all have similar intermolecular attractions, so they all bunch together and form kind of these little spheres. So they're surrounding these hydrophobic tails with the ends of the molecules that really like to interact with water. So these are floating around in this solution. Now, I've made this really huge compared to the container that it's in, and that's not really to scale, but just so you can picture what's happening. So what's dirt made out of? If you're trying to clean something, if you're trying to wash your hands, you're trying to wash your clothing, a lot of times dirt and stains are going to be things like oil and greasy food and dirt. So the stuff we're trying to remove is very similar to these long hydrocarbon tails. So if I have a piece of dirt here, those hydrocarbon tails will surround it because they're attracted to it, and these little heads are attracted to the water. So they surround it. Now the key thing here is that the presence of these hydrophilic ends, the ends that like to interact with water, the fact that they're there keeps that piece of dirt floating around in the solution so that it doesn't clump up in the bottom. This allows us to rinse that away when you're washing your clothes or washing your hands. You rinse that off and the dirt goes away surrounded by that detergent. So this happens, we clean our clothing, and then we come along, and I use Downy, and I think most of you use fabric softener when you're washing your clothes. And fabric softener is very similar to the Tide or the detergent that we just used. So I'm going to draw what Downy looks like, at least from the information I've been able to find. So in the Tide, this is a 12 carbon long chain. In Downy, 1, 2, 3. In Downy, it's an 18 carbon chain. So this is a C18. That just means 18 carbon chain with all the hydrogens on it. And not only does it have one long hydrocarbon chain, it has two. All right, so I've got two long hydrocarbon chains attached to this nitrogen with two other groups, and we don't care if they're hydrogens or other carbon groups. But the bottom line with this is, after my clothes get clean, they're kind of scratchy. So if you've ever washed your clothes and dried them and not put any fabric softener in, they're a little rough. So the way that you soften them is you throw this compound into water during the rinse cycle. It does the same sort of thing with the long hydrocarbon tails being kind of oily and trying to avoid the water. And then we have this other end that's attracted to your clothing. So you've got that end, and I'm just going to draw a line here. So here's the surface of your clothing. And if this little molecule sticks to your clothing, then you've got these long oily tails that come up off of that surface. So these organize themselves on your clothing. And then you rinse away any of the extra and you dry them. And when you feel your clothes, they feel smooth now. Well, what does oily hydrocarbon stuff feel like? It feels smooth. And that's what you're feeling when you feel that you're smooth or softened clothing. So this is all there and it's stuck to your clothing. Have you ever put too much Downy into a load of towels and then you try to dry something with that towel and it doesn't absorb any water? It all beads up on the surface. Well, it's because you put too much Downy in there. Remember, these hydrocarbon tails, they don't like water. So if I tried putting a drop of water here, it's just going to bead up and sit there. It's not going to be absorbed by my cotton towel down here. It's never going to see the cotton towel. It's got all this stuff in between it. So I think that's pretty fascinating that all of this comes out of just opposite charges attracting and intermolecular forces. But not only that, why don't you ever put Tide and Downy into the washing machine at the same time? It'd make things a lot easier, right? until they made those little Tide Downy ball, or those little Downy balls that you throw in and then they release the Downy during the correct cycle. Before they did that, you had to run downstairs, throw in the Tide when the wash was halfway done. And I still remember when that was the case. So it's much handier now. So let's say I've got these two compounds. Let's say that I tried putting them both together into the wash water and just see what happens. So if I put those together, what happens with this stuff? When it dissolves, that sodium floats away. That's in the solution somewhere, but we don't care about it because we know most sodium compounds are soluble, if you look at your solubility table. So I've got this charged group here with this long hydrocarbon tail that really doesn't like water and really wouldn't dissolve by itself. And then I have, in this Downy, I've got this positively charged end, again with two really, really long hydrocarbon tails that don't interact well with water. If I put both of these things into the solution at the same time, what happens? And remember, this floats away, and we're not worrying about that. Opposite charges attract each other, and I would end up forming a great big glob of hydrocarbon gooey mess. So let's say that this interacts with the positive end of the Downy with its long hydrocarbon tail, and I'm not going to count all of those carbons out because it's really not important. So I've got this positive end reacts with the negative end, and they form a precipitate. So this stuff precipitates out of solution because all the water sees are really, really long chains of carbon and hydrogen. The charges are up here interacting with one another and not with the water. So this stuff becomes a big gooey precipitate, and so it would just make a really big mess on your clothing, and you really wouldn't want to try doing that. Your shampoo and conditioner work under the same sort of principles. So your shampoo looks a lot like this, your conditioner looks a lot like this. You do them separately. You condition your hair and basically leave the stuff behind so it feels smoother and less staticky. The only other thing I want to point out is, why doesn't detergent work very well if you have hard water? So we'll get rid of our Downy drawing here. So let's say that I've got hard water and I throw my Downy into the hard water, or sorry, throw my Tide into the hard water. Hard water just means usually that I have some calcium floating around, calcium ions. So what happens with the calcium ion and this detergent? And I want you to think back to our solubility chart. And sodium, when it interacts, sodium ions, when they interact with other negatively charged ions, don't form precipitates. They just aren't strongly enough attracted to those other ions. But calcium is one of those frequent exceptions, one of those ions that forms a lot of precipitates. So if we put calcium with these ions, they end up precipitating out of solution, and they don't stay floating around and interacting with the water because we've formed that solid ionic compound. And again, if you have any experience with having hard water, you make this scummy, soapy goo that sticks to like your bathtub or your washing machine or your clothing. And that's because of the formation of a precipitate again. So that puts together our information from solubility early on in the semester, precipitation reactions, and now our intermolecular forces, and I think gives you some fun facts to go and fascinate your friends with. And, if not, you can just kind of enjoy them by yourself and not tell anybody else and admit that you're kind of a geek. But have some fun with that, explain it to somebody else, and I think you'll have a good time. So that was just some fun information, and if you have any questions, let me know.